Hello, my name is Wouter. I am a PhD student here at the University of Eindhoven, and I'm going to present to you what's new with GraphPPL.jl. So first, let's talk about what is GraphPPL.jl. I'm going to piggyback off of Bert's keynote this morning. GraphPPL is a probabilistic programming language used in the RX-infer Bayesian inference ecosystem. It is the front-end design-specific language for the RX-infer inference engine, and it is a language for specifying probabilistic graphical models. So the first thing we did with GraphPPL is that we made it completely inference backend agnostic. So the new version of GraphPPL completely does not depend on the RX-infer inference engine. You can specify your probabilistic generative model, and it will output a factor graph for you. So it will give you a factor graph representation of your model. In order to do this backend agnosticism, we implemented what we call a plugin system, which is basically just an extensibility system for backend developers. For example, RxInfer.jl, which does variational inference, uses a variational constraints plugin in which you can specify constraints on the variational posterior, which is then used by the inference backend to do Bayesian inference. So this gives us a very general, lightweight, but still customizable data structure with which we can represent probabilistic graphical models, and it can be used by any inference backend. So if we look at the syntax of GraphPPL, we can specify a generative model with the add model macro. Here I have a model that is written in the previous version of GraphPPL. So as you can see, we define a bunch of constants. We define x as a random variable. We define y as a data variable. And then we can specify a probabilistic relation with the tilde syntax. Now, in the new version of GraphPPL, we can actually infer whether or not something is constant, data, random, whatever. So all these lines at the top, they all go. I don't like them. Similarly, we have this x0 argument, which is presumably a probability distribution because we extract its mean and covariance and then pass it into a multivariate normal again. I also don't like that, so it goes. Also the parameter n, which is supposed to be the amount of data points, we can actually infer the amount of data points when we get data, right? We know it. So it also goes. So that means that the new syntax in GraphPPL for the same model in GraphPPL 4 is a lot shorter. So it does not contain all this boilerplate that we had previously. Another thing that we support now is nested model support, what we call nested model support. So as you can see, we have these two lines. Do you see? Can I? No, I don't have a cursor. But we have the S1 and Y1, which are being initiated as a Gaussian distribution. And then we have the same two Gaussians in our inside the for loop again. So we can take these two lines out. We can make a separate model. We call it submodel. Include those two lines, and then use this submodel, this GraphPPL model, inside a larger model. So we can use any GraphPPL model as building blocks of larger GraphPPL models. Now, in this example, it's obviously a bit overkill, right? But let's go crazy with this, all right? So you guys have all heard of neural nets. You all know that, hopefully, that a neuron, an artificial neuron, is just a dot product between a weight vector and an input. We add some bias, and we push it through an activation function. So here we have the GraphPPL model for a single neuron. We instantiate a bunch of weights. We put a prior on it. We take a dot product. We add a bias, and we pass it through a ReLU. Then we can create a neural network layer by just copying this neuron n times. So we have still our in, our out, and n. We copy this neuron n times. And if we then want to make a multi-layer perceptron, we stack a bunch of neural network layers. So this is like 15 lines in total. And if you actually instantiate this model, you actually create 28 neurons, more than 300 factor nodes, with over 1,371, exactly 1,371 connections in your factor graph. So you can spawn really big, complex models with a very simple syntax. So that's my talk. If you want to play with this, please check out RxInfer for a fully integrated example with an inference backend. So that's nice. You can run inference in your models. If you like the progress, give us a star on GitHub. That really supports us. And if you have any questions, I'll be happy to take them.
Thank you, Wouter. We have some extra time for questions indeed. Thank you for the simplification in the programming work environment. Anybody curious to learn more?
So which kind of deterministic operations are allowed in this model language?
Basically, so for the model language, you can put any deterministic operation. Actually, we leave it to the backend developers to determine whether or not something is deterministic or stochastic. For us, it's just, well, we create a factor node or not. However, if we have something that is labeled as a deterministic relation and all the arguments are known at compile time, we'll just compile it away. Like, we won't create any factor nodes because everything is known, right? We can just evaluate it and push it in. But we leave it to backend developers to say, well, this is deterministic, this is stochastic, and then it's up to backend developers to see how you handle this.
Maybe 2 or 3 more questions.
Thanks for the talk. Yeah, just a general question. What's next for GraphPPL?
That is a very good question. I'd say, so my work will now mostly focus on the actual inference, right? So it kind of depends what features people will put in. So probably I would want to have more plugins. So sort of debugging plugins or a way in which you can plot your generative model, and it looks nice, so that you have more debugging functionality in GraphPPL.
So this model language is then actually quite similar to the Turing model language, right?
It's very very similar.
Would there be a perspective that we maybe have one layer up so that we just have the model language, and then you decide compile this in a graph way or in a Turing way, and then we go to different inference engines so that we get to a common model language and then kind of different intermediate representations?
So this work is actually an attempt to do that, and with the graph as sort of the compile target. So, well, if I see the Turing guys around, their talk is after mine on the main stage. I'm going to go there. If they would want to do the work, they could adapt this as their language, and we would have this universal system. But yeah, it takes some work, right? Because it's a different language. But that's why we made it backend agnostic.